maybe you are considering a career in machine learning engineering. But what does a machine learning engineer actually do? Here's the funny part. It's not so obvious based on just the name of the position. When you check the US Bureau of Labor Statistics, the only remotely relevant position is data scientist, and based on its description, it's supposed to cover any data-related role. It isn't better when you look at job offers. Let's take Google for example. There's a machine learning software engineer who focuses on low-level programming related to ML models, or a machine learning engineer for Gen AI who is expected to optimize models and agentic workflows, optimize ML infrastructure, and develop large-scale AI-powered platforms. Quite a lot to do. It can be intimidating, but let's focus on the general consensus of what that role embodies, which is aligned with my personal experience. Usually the responsibilities include reviewing scientific papers and other related resources to gather ideas and keep up to date with the field, searching for public datasets and designing custom data collection processes, developing data processing and model training pipelines, designing and conducting experiments, evaluating solutions, developing software for interacting with models, deploying and monitoring ML solutions in production. Of course, in some teams, those tasks may be distributed across different roles, but in general, you should be prepared to handle all of them at least to some degree. The one thing you can be sure of is that there's a lot of software engineering involved. Google published a paper about technical depth in ML with a diagram that accurately visualizes the proportion of pure model-related tasks compared to everything else. So, if you wondered whether programming skills are important for ML roles, then answer is yes, they're absolutely crucial. You don't have to be a senior Python developer to do ML, but you should be a decent programmer. But let's leave that for later and focus on the machine learning engineer's responsibilities, breaking them down one by one. Even if you're working on the same problem for years, you'll have to keep up to date with developments in the field. New findings might be worth redesigning your whole approach or changing the angle from which you are tackling the problem. Usually, reviewing what's out there is the initial step for any ML task. Chances are someone has worked on something similar and you can at least get inspired. And who knows, maybe they linked their GitHub repo in the paper and the code still works. When reviewing literature, the goal isn't to find flaws, re-implement papers, or propose your own improvements. It's simply to understand what people tried, what seemed successful, what might be a low-hanging fruit worth testing, what changes to expect, and whether anything already implemented can be reused. And you won't rely exclusively on archive.org. Most of the time, you'll be just Googling things. For inspiration, Medium posts and YouTube videos can be as useful as NoRips publications. When it comes to datasets, it's rare that the data is ready and waiting for you. You will often have to secure it yourself. Sometimes something similar is available publicly, sometimes it requires using APIs, and sometimes it involves designing a whole data acquisition and annotation process. You would be surprised how often you deal with special equipment to solve very specific needs, especially in vision projects. Maybe flying drones over crop fields for hyperspectral images, maybe accelerometers on metal structures, maybe sensitive microphones for non-intrusive wildlife monitoring. Once you have data, you will still require processing, usually over multiple steps, before you can use it for training. And if you identified multiple promising approaches, they may all expect different input formats, so you will have to handle that too. Initially, you can survive with spaghetti code, but as the pipeline grows, you'll realize that a non-trivial amount of software engineering is inevitable. Here's where the theory you learn comes in. Generic solutions you can just feed data and labels into serve as a nice baseline, but they rarely solve your specific problem. They may miss accuracy targets, latency requirements, or resource constraints. Your main task is to generate ideas for what might work, what is promising within your available time and budget, and what you expect from a given experiment. Based on the outputs, you may need to adjust your approach, reevaluate ideas, or worst case, conclude that your data collection was flawed and needs to be redone. It also involves a lot of debugging, the worst kind. Everything may work technically. Models may train and produce outputs, but results may still be subpar, not because the idea is wrong, but because there's a bug somewhere and your data isn't being processed the way you intended. When evaluating your solutions, you must think about real-world scenarios. Choosing adequate metrics matters, for example, avoiding plain accuracy for imbalanced datasets. But more importantly, you must understand what is important from the business perspective. Sometimes missing signals is acceptable, but false positives are not. Sometimes it's the opposite. Sometimes consistency across conditions matters more than accuracy. The challenge is designing evaluation that reflects the production environment and measures what the client cares about. Your stakeholders may initially be satisfied with static data, a CSV file or sample outputs, but that usually doesn't last. They may not trust those results, or they want to stress test the solution themselves. Often, they are not technical domain experts or business people who won't run your scripts directly. For that reason, you may need to set aside time to create an application with a usable graphical interface, so they can interact with the model themselves. Depending on your model, this can involve deploying a Triton server or using cloud services, but very often it's just a simple web app hosted somewhere so your client can play with the solution. At some point, the time comes to test your model in the real environment. It might be deploying it in the cloud and switching traffic to it, but in more complex scenarios, it means physically going to a factory where the vision system is installed and running tests there. Sometimes it's even more adventurous, like getting on a boat, traveling 500 kilometers offshore, and debugging how your model classifies marine organisms from an underwater camera. Most cases won't be that dramatic, but scenarios like that aren't rare either. And whatever the setup, you'll need a mechanism to monitor performance in real life. I hope this gives you a general idea of what you might be responsible for in this role. Most of the time it's just programming, but you'll deal with different kinds of problems and with the non-deterministic nature of your solutions. Sometimes a week of tinkering and discussions with your team results in just a single line of code changed. Often you will have to get familiar with niche domains to gather insights from experts. And you can't be afraid of getting your hands dirty with tasks, technologies, and tools outside your main expertise. I know that for many practitioners, this outline may seem like a romanticized version of the actual job, and I get that. An ML engineer spends a lot of time on software development, but I personally have had many opportunities to work in the field when doing computer vision projects, and I'm not special in any way, so I'm sure you will have such chances too if you're interested. Please share your own experience, it may help others who are considering whether ML engineering is for them, and thank you for watching.